The first one is passive solar design. Passive solar design refers to the use of the sun's energy for the heating and cooling of living spaces by exposure to the sun. The idea is when the sunlight strikes a building, the building materials can reflect, transmit, or absorb the solar radiation. In addition, the heat produced by the sun causes air movement that can be predictable in designed space. Unlike active solar heating systems, passive systems are more simple and do not involve substantial use of mechanical and electrical devices such as pumps, fans, or electrical controls to move the solar energy. So basically, there are 5 basic elements to achieve a good passive solar design. The first one is an aperture or collector. It is a large glass area or basically a window through which sunlight could enter the building passively. The aperture should be facing within 30 degrees of true south and should not be shaded by other buildings or trees during the heating season. This is because during the heating season, the house is going to be really cold and we need the sunlight to get through the window and warm up the floor. And the heat absorbed by the floor will be transferred and will be benefit during night time or cold time. The second element is an absorber. If you want to have a good passive solar system in your design, you can use materials that made of hard or darkened surface, which is used as a heat storage element for your house or buildings. The surface that absorb the heat could be masonry wall, floor, or water container, which sits in the direct path of sunlight. And the sunlight hitting the surface is absorbed as heat to warm up the buildings.
The third passive solar design basics is the thermal mass. Thermal mass is the material that retain or store the heat produced by sunlight. While the absorber is an exposed surface, the thermal mass is the material below and behind this surface. Next is the distribution. The distribution is the method by which solar heat circulates from the collection and storage points to different areas of the house. A strictly passive design will use the 3 natural heat transfer modes: conduction, convection, and radiation exclusively. In some applications, fans, ducts, and blowers may be used to distribute the heat through the house.
The last element is a controller. The controller here can be varied. It can be the louvers, roof overhangs, shade, porch, or more and more. Basically, it is used to shade the aperture or the window area during the summer months. Besides that, a manageable ventilation system, low emissivity blinds and awnings also can be used to control all these overheating problems. All these simple add-ons are actually really practical and efficient to cooling down the house. Passive solar design also can be used in 2 kinds of ways, either for passive solar heating or passive solar cooling. So for the first one is passive solar heating. The goal of passive solar heating system is to capture the sun's heat within the building's elements and to release the heat during periods when the sun is absent, while also maintaining a comfortable room temperature. The 2 primary elements of passive solar heating are south-facing glass and thermal mass to absorb, store, and distribute heat. The second one is passive solar cooling. Passive solar cooling system work by reducing unwanted heat gain during the day, producing non-mechanical ventilation, exchanging warm interior air for cooler exterior air when possible, and storing the coolness of the night to moderate warm daytime temperatures. At their simplest, passive solar cooling system include overhangs or shades on south-facing windows, shade trees, thermal mass, and cross ventilations. Now, move on to the active solar design. Active solar describes energy systems that capture the sun's energy and store it in some manner for later use through mechanical or electrical means. The 2 basic types of active solar design are through electrical system and thermal system that heat liquid for domestic hot water. There are 2 types of active solar design, which are the renewable electricity system and solar thermal systems. Renewable electricity system usually talks about the panel solar itself. It usually installed on the roof to generate electricity by collecting heat from the sun and storing it in the form of water photovoltaic panels. The panels are made of thin slices of monocrystalline or polycrystalline silicon onto glass surfaces that are interconnected into arrays. It is used to generate direct current electrical energy, typically between 12 and 48 volts. Optimal orientation, slope, and weather patterns are really important to achieve good solar energy accumulation. And the panel usually will be installed facing to the south with approximately 30 degrees above horizontal. The benefits of using this system, there are many companies offer lease program where they will install and maintain your panels, while the residents benefits for the power produced and reduce energy bills, while the company gather any rebates. The second one is the solar thermal system, which is used to collect heat from the sun and store it in the form of water. This kind of system usually used in a region that do not experience hard freeze temperature, and it must be pumped mechanically from the tank to the solar collector on the roof.
Now, moving on to building integrated active and passive solar design. The combination of both is an evolving science in building technology where the hybrid design is basically able to maximize the energy output and reduce system consumption like AC and lighting and so on, where it's employing facade integrated renewable energy technology. When it comes to the application of such solar devices, the design may vary according to the person in charge. So the design can be hidden, aesthetically pleasing, or even appearing as an architectural concept, where the figures shown show the solar device on the building facade and the other one shows the solar device at the roof. Where on the building facade, these devices play a critical part in its influence on the engineering system performance, as well as, of course, on energy use other than being the building envelope. And as derived from the active and passive solar design, the combined photovoltaic thermal technology integrates the solar, thermal, and photovoltaic technologies into a single device, through which thermal and electric power can be generated simultaneously in a controlled manner, as can be shown in the infographic. A photovoltaic thermal system requires a PV module, a channel, coolant, whether air or water, and a collector. The classification of PVT technology is shown here in the graph, where a device has a collector type, whether a flat plate or a concentrator type, a coolant type, whether air, liquid, or a combination of both, and different material types. Now, when it comes to the selection of which type of photovoltaic thermal collector and system is more useful and required, it mainly depends on the geographical location and it's decided case by case. For example, in high latitude areas with low solar radiation and colder climates, space heating is required most of the time, and air-based photovoltaic thermal system can be used and be more cost-effective. Where at locations with higher solar input, the water-based PVT option is more suitable and useful, as well as the photovoltaic ventilated glazing technology, where it can save energy through AC load reduction, more favorable daylight penetration, solar energy utilization, and improving disability glare and local thermal discomfort caused by radiation asymmetry. By cooling the photovoltaic surface with the help of air or water as a flowing fluid or a coolant, the system is significantly improved, where the performance of the hybrid photovoltaic thermal system is measured in terms of thermal, electrical, and energy efficiencies of the system, and the thermal efficiency can be enhanced when front glass is provided. The following systems are the three discussed in our journal, with the flat plate base, air base, and water or liquid base. Figure 1 shows a building integrated photovoltaic thermal collector unit with an array of heat pipes attached to a thermal absorber with the solar cells laminated at the top surface. The condenser end of each heat pipe is inserted to a manifold heat exchanger where the feed water stream passes through. And the thermal efficiency is enhanced and the facade thermal insulation is improved in this design. While Figure 2 shows the configuration of a photovoltaic ventilated glazing for use in warm climate, the fenestration system has two glazing assemblies where the inner one is simply a clear glass panel. The outer assembly carries a photovoltaic glass panel with the vent opening at its top and bottom ends as shown in the figure to provide the buoyant flow of ventilating air from the outside on sunny days. With the heat-absorbing effect of the semi-transparent photovoltaic glazing, together with the cooling airstream in the cavity, The solar transmission to the indoor space is much reduced in this design of the device. And as an economical alternative, one promising design is the replacement of airflow channel by a colorless liquid flow like water. In the liquid flow option, a thermosiphon-induced liquid stream flows up the cavity to the heat exchanger at the top for feed water heating, where Figure 3 shows an indicative liquid flow circuit. Solar transmission through glazing is then reduced, space cooling load is lowered. Natural light is enhanced since the liquid layer has negligible effect on the visible light spectrum, with thermal load reduction, natural light preservation and utilization, and useful heat gain for hot water supply in one go. To quickly summarize and conclude, the building integrated active and passive solar design asks for the consideration of all building components and service systems have to be well coordinated and maintained, where this can be sometimes a main challenge to overcome, yet it has an escalating importance in services engineering due to its significant influence on the engineering system performance and energy use. And as we evolve and have more interest in zero carbon and positive carbon building developments, it's important to maximize the renewable energy outputs and thus favor the use of hybrid generating systems like the combined passive and active solar design as shown here. Thank you.